In this video, we are going to look at how to solve partial differential equations using the method of separation of variables. Now, let us consider a partial differential equation where z is the dependent variable and x and y are the independent variables. Then the basic idea or the basic assumption behind this method is that the solution of this partial differential equation, that is the solution is z of xy, can be written as a product of two functions, say x and y, where x is a function of x and y is a function of y. Okay, so the basic assumption is that z can be written as a product of two functions where one is a function of x and the other is a function of y. That is, it can be separated in such a manner. Now, you consider any partial differential equation which is linear. So that is, for this method to work, the partial differential equation should be linear and homogeneous. So it works well for PDEs which are linear and homogeneous, and the boundary conditions should also be linear and homogeneous. Now let's just see what we mean by linearity. Linearity means that the dependent function, say z, and its derivatives, that is zx, zy, zxx, zyy, etc., all these terms should be linear, in the sense that there should not be any z square term, there should not be any x square term, etc., and these should not be as products, zx into zy or zx into z. Such terms should also be not there in the PD. Homogeneous. Now the next thing is homogeneous. Homogeneous means that, suppose I am writing zx plus zy equal to x square plus y square, then this is non-homogeneous because this x and y terms are there individually without they are not as a coefficient of zx or zy. So this term, this term should not be there. Okay, there should be only z, zx, zy terms. Of course, the coefficients of these terms can be x or y, they need not be constants. That is not a problem, but this x and y terms should not stand alone. That is what we mean by non-homogeneous. So it should be homogeneous means such terms should not be there, but as such. So what this how this method works, okay, that is, suppose you are having a partial differential equation. Say I'm just calling some partial differential equation, maybe zx plus zy equal to 0. This is, I'm not going to use this differential equation, so just to illustrate what we mean by a partial differential equation, I'm just writing this. That is, in other words, it will be dou z by dou x plus dou z by dou y equal to 0. Okay, this is what we mean by a partial differential equation which is linear. It can be dou square z by dou x square, there can be x into dou square z by dou x square, all these things can be there. Now how this method works is, we have to first assume that it has a solution, that is z of xy. The solution of this PDE, z of xy, can be written in the form x into y, where capital X is a function of x and capital Y is a function of y. Now if this is understood that capital X is a function of x and capital Y is a function of y, we can just rewrite this as z equal to x into y, where we know what we mean by z, capital X and capital Y. Now what is zx then? Zx will be x dash y, because here you see x is a this capital X is the only function which contains x terms. Y, when I partially differentiate with respect to x, y can be treated as a constant. So this is the only term which has x, and this term is a function of y. So we can just write the derivative as x dash y. Similarly, what will be zy? Zy will be x into y dash. Now when I'm partially differentiating it with respect to y, what happens is this x term here becomes a constant. It can be treated as a constant. This is the only part where we have a function of y, so we only need to differentiate that part, so that it becomes x into y dash. Similarly, what will be zxx? Zxx will be x double dash y. What will be zyy? Zyy will be x into y double dash. Now these are the derivatives, partial derivatives of z, provided that we assume that z is x into y. Now the next, this is the first step that we have to do, that is we have to assume that it has a solution in this, a product solution of this form. Now next thing is you have to substitute these terms, all these terms z, zx, zy, or all these terms into the given partial differential equation. Okay, now when I substitute that and simplify it, what we will get is we will be able to reduce it into two ordinary differential equations. We'll be able to reduce it into two ordinary differential equations, one containing capital X terms and the other containing capital Y terms. Now if you solve these two ordinary differential equations, you will get the solutions capital X and capital Y. Back substituting that here, you will get your final solution Z. Now this is the method. We will illustrate this method using an example. Okay, so let's just look at a question here. So just consider this question. Let us consider a partial differential equation zx equal to 2zy plus z. Now with the boundary condition z of x0 equal to 6 into e raised to minus 3x. Now let's see how we can solve this. Now the first assumption, as we discussed, is we are going to assume that it has a solution of the form z equal to capital X into t. Then zx will be here it should be y. Okay, y of y. Now z equal to capital X into y. Now zx is x dash y and zy is xy dash. These are the partial derivatives, because when I'm partially differentiating this equation with respect to capital X, this is the only term which is a function of x. This can be treated as a constant, so it becomes x dash y. Now when I'm partially differentiating with respect to y, it is vice versa. This term here can be treated as a constant. This is the only part which is a function of y, so it becomes x into y dash. Now we are going to substitute all these things into the given PDE, and then we will find the solution. So we'll just see what happens. Okay, so the question was zx equal to 2zy plus z. Okay, so we have zx equal to 2zy plus z. Now substituting, what is z? Z is xy. What is zx? Zx will be x dash y. What is zy? Zy will be xy dash. Okay, these are the substitution that you have to make. Now from this equation, what I'm going to do is I'm going to take this term onto the left hand side. Now what will happen is I can take y common outside, so it becomes x dash minus x into y. That is x dash y minus xy. I've just taken y common outside, so it becomes x dash minus x into y is equal to 2 times x y dash. Now what I'm going to do is I'm going to collect all terms involving x on one side and all terms involving y on the other side. So left hand side I'll be left with x dash minus x by 2x, and the right hand side I'll be left with y dash by y. Now here left hand side is a function of x and the right hand side is a function of y. Okay, y dash by y, it only has y terms. X dash minus x by 2x, it only has x terms. Now both of these terms will be equal if and only if it is equal to a constant. Okay, so we can take that this is equal to a constant. I hope you have understood what I said. That is, on the left hand side we have a function of x, on the right hand side we have a function of y. Okay, so suppose I'm just taking, for example, y of 2. I'm just taking a specific value here. Instead of y, I'm taking 2. Now whatever be the value of x I substitute here, this whole term will be equal to y dash of 2 by y of 2, because in this relation you see here, x and y are independent. I can give any value to x and any value to y. So for y, always I'm going to give 2, and for x I'm going to give different values. Even then this equality should hold. So what that means is that this y dash of 2 by y of 2 is a constant. If I take it as k, then this relation is equal to k. Okay, so to sum it up, here x and y are independent variables, and a function of x and a function of y are equal, means that relation is equal to a constant k. Okay, now if you have understood that, we will move forward. So that is the basic assumption that we are taking here. We have x dash minus x by 2x is equal to y dash by k, y, which is equal to a k. Okay, this we just explained now. Now from these two, we will be writing down two ordinary differential equations. What we have is x dash minus x by 2 x equal to k. That is the first part I'm taking. I'm only taking this first part here, that is x dash minus x by 2x equal to k. Okay, so I'm taking that part, x dash minus x by 2x equal to k. That implies, suppose if I divide that by x, what I'll be having is x dash by say 2x equal to by x minus 1 equal to 2k. I'm just taking 2 to the other side and dividing the whole terms by x. That implies x dash by x is equal to 2k plus 1. Now what will happen is this x dash by x, integrate both sides with respect to x. I have to integrate both sides with respect to x. So integrating both sides with respect to x, I'll be left with x dash by x, that is I'll be left with log x. Integral of x dash by x is log capital X is equal to 2k plus 1 is a constant, so 2k plus 1 into x. Integrating the right hand side, so integral of a constant is constant times x plus c. So instead of c, I'm going to use log c. Now what I have to do is I will just write in terms of x. So x will be equal to c into e raised to 2k plus 1 times x. This is our capital X. That solution is written here. So you'll have x as c into e raised to 1 plus 2k times x. Similarly, we will be considering the second equation also. Now considering the second part, that is this part. Considering the second part, that is we will take y dash by y equal to k. So let's see what happens. So y dash by y equal to k. Now integrating both sides, I'll get log y dash is equal to kx, ky plus log c dash. That implies y so we will be left with y is equal to c dash into e raised to ky. Now that is what is written here. Okay, y equal to, sorry, here it is y equal to c dash into e raised to ky. Now we'll go back to the final solution. If you remember, the final solution is z is equal to capital X into y, where x we found that it is equal to c into e raised to 1 plus 2k times x, and y is equal to c dash into e raised to ky. So the final solution will come out like this. Now what we have to do is we have to use the boundary conditions. We have to use the boundary conditions to find this constant c dash and k. Now we are given with the boundary condition z of x0 equal to 6 e raised to minus 3x. Now in this we have to substitute y equal to 0. So what will be what we'll get is, so when I substitute y equal to 0, c dash into e raised to 1 plus 2k times x. 1 plus 2k times x into e raised to 0 is 1. That will be equal to 6 e raised to minus 3x. This is what we will be left with. Now equating both sides, the constant c dash will be equal to 6 and 1 plus 2k is equal to minus 3. E raised to 1 plus 2k x is equal to e raised to minus 3x. So we are left with two things. One is c dash is equal to 6 and we'll have 1 plus 2k is equal to minus 3. Now from this I'll have 2k is equal to minus 4 and k is equal to minus 2. So those solutions are written here. Now we will have from that the final solution is z equal to 6. C dash is given as 6, so 6 into e raised to minus 3x into e raised to minus 2y. I'm just substituting c dash is equal to 6 and k is equal to minus 2. Okay, now z is equal to 6 times, I'm just writing the exponent of e together, so e raised to minus 3x plus 2y. Now this is how you have to solve the solve a question using the method of separation of variables.